Hello everyone, so today we're going to solve a problem from the Sharon's book series, okay, of the 3000 solved problems. So in this problem specifically we have a calculus case, right, where we're given that a car is forced to move along the x-axis so that the displacement is given by the function x, right, is equal to 30 plus 20t minus 15t squared, where x is in meters and t is in seconds. Now the question is divided into A, B, C, and D. So A is find an expression for the velocity and for the acceleration, okay, and is the acceleration constant? Okay, what are the initial position and initial velocity of the car? What and at what time and what in distance from the origin is the velocity is zero, okay? So when the velocity is zero, what is the time and what is the position? At what time and location is the velocity negative 50 meters per second? Okay, so we're going to go ahead and start part A. Part A asks us to find an expression for the velocity v. Well, we know that if we have the position function, we know that the velocity will be, okay, so v will be the first time derivative, okay, of the position function, okay, so that will be, so let's just put this here, part A, okay, so that will be the derivative, okay, first time derivative of 30 plus 20t minus 15t squared, okay, which will be, okay, derivative of a constant 0, derivative of 20t is 20, and then we have minus 30t, okay, that will be our velocity function, so we have to keep it in mind, we're going to use it later. Now we're going to find an expression for the acceleration of the car. Okay, so we know that the acceleration is the first time derivative, okay, of the velocity, which is also equal to the second time derivative of position, right? So d squared x over dt squared, which will be, okay, d over dt of that, the velocity function, which is over here, right? So will be 20 minus 30t, okay, the derivative of 20 minus 30t is just negative 30, okay, meters per second squared. That tells us something, if that's the acceleration function, right, if that's equal to a, all right, so that means that the acceleration is constant, right, it's always negative 30 meters per second squared. Good, so we can say yes, okay, for that question over here. So acceleration is constant because it's just negative 30 meters per second squared. We're going to move on to part B. What are the initial position and initial velocities of the car? Okay, so we have to think about this. Well, not really. We know that the initial position and initial velocity occurs when t equals 0. So how about we set those functions, we set the t value, okay, of those functions equal to 0. So let's go to part B. So to find initial position, x0, okay, that's equal to 30 plus 20 times t, and t in this case will be 0, okay, so we have to let t equal to 0, okay, times 0 minus 15 times 0 squared, alright, so that cancels out, right, that's just 0, and then we're left with 30. So x0 is 30 meters. So the initial position, okay, will be 30 meters. Okay, good. Now let's do the initial velocity, okay, initial velocity v. Okay, so v0 also occurs when t goes to 0, okay, when t is equal to 0. So we have the velocity function over here, which is 20 minus 30 times t, and in this case t is 0, okay, so that just goes away, and we have that v0 is equal to 20 meters per second. Okay, all of this is in SI units, okay. Now we're going to move on to part C. Okay, so part C asks, at what time and distance from the origin is the velocity 0? Okay, so we're just going to go ahead and set the velocity, okay, equal to 0, because we already know the function of the velocity in terms of time. So let's go ahead and set v equal to 0, which is, okay, the same as 20 minus 30t equals 0, right? And we solve for t, right? We want to find the time so that we can find the distance from the origin, so that when the velocity is 0. So we bring 20 to the other side, we divide by negative 30, and we get that t is equal to, okay, 2/3 seconds. Okay, very well. So that's the same thing. So that's about 0.67 seconds. Okay, that's the time. Okay, now let's find the distance from the origin. Okay, when the velocity is 0. So we're just taking the velocity function and we're setting the time of that velocity function equal to 2/3 seconds, or 0.67 seconds. So we have v, right? So we're finding the the time and the distance. So we're setting the position function. Excuse me. We're setting the position function. We're gonna let t equal to 2/3 seconds, right? Because we've already found that from the velocity function. So we don't have to use the velocity function again. So let's do that. Okay. So what is v? Okay. What is x when it's equal to 30 plus 20 times 2/3, okay, minus 15 times 2/3 squared. Okay, so we're going to evaluate that value. So let's just go on. So we'll have the position function over here, and so x is equal to, we're gonna let t equal to 2/3, right? So 30 plus 20 times 2/3 minus 15 times 2/3 squared. Good. Now that's equal to 20 times 2 is 40, so 30 plus 40 over 3, right? Minus 15 times 4 over 9. Okay, good. Because 2 squared is 4, 3 squared is 9. Okay, 15 times 4 is 60, but we can simplify this, right? This divided by 3 is 3, this divided by 3 is 5, and we have 5 times 4 is 20, 20 over 3, so we have common denominator. Let's multiply this by 3 as well, so we have x equals to 90 plus 40 minus 20, okay, everything divided by 3, so here we have 20 plus 90 is 110, so that's 110, okay, divided by 3, and that's going to give you about 37 meters. Okay, so that's about 37 meters. So that will be the distance from the origin when the time, okay, is 2/3 seconds, or 0.67 seconds, and the velocity is 0. Okay, so that's when the velocity is equal to 0. Okay, very good. Now let's do part D. Part D asks, at what time and location is the velocity negative 15 meters per second? So we're being asked for position and for time. Good. So let's go ahead. And since we know the velocity, we can set that equal to our velocity function. So 20 minus 30t equals to negative 15 meters per second, right? So we have the 20 minus 30t is equal to v, and we're going to let v equal to negative 50 meters per second, right? So 20 minus 30t is equal to negative 50 meters per second. Well, we don't have to write 50 meters per second because we already know it's in SI units. We'll just do that at the end. Now we solve for t. So this is going to give us, okay, we bring the 20 to the other side, we get negative 70. Negative 70 over 3, that's 7/3, so t equal to 7/3 seconds. Okay, and that's about 2.3 seconds. Now, we already found the time, that's 2.3 seconds, okay, when the velocity is negative 50 meters per second. Okay, now we are going to find the location using the position function given the time, right? So, the location, or position, is equal to 30 plus 20 times t, and we're going to let t equal to 7/3, right? So 7/3 minus 15 times 7/3 squared and we're going to multiply this out. So this is 140, so 30 plus 140, okay, divide by 3, minus 7 squared is 49, 3 squared is 9, okay, times 15. We can simplify this again, so 9 divided by 3 is 3, and 15 divided by 3 is 5, 49 times 5, okay, so that's going to be 245, so x is equal, let's multiply this by 3 so that we have common denominator. We have 90 plus 140, okay, minus 245, everything divided by 3. 90 plus 140 is 230. 230 minus 245 is negative 15. Okay, so we have x equals to negative 15 over 3, which is just equal to negative 5 meters. So when the velocity is equal to, when the velocity of the car is equal to negative 50 meters per second, the time, okay, has to be 2.3 seconds. So from the start, from t equals 0 to t equals 2.3 seconds, the velocity will be negative 50 meters per second exactly at 2.3 seconds. And it travels a distance, or from the origin, of negative 5 meters, right? So it will be the net displacement, the location, okay? So that's it for today. I hope you enjoyed this first physics video. Okay, so this is just one of the infinitely many applications of calculus, right? But I think the most important things we learned were that the first time derivative, right? First time derivative, so d over dt, let me actually do it in green so that it's more emphasized. So d over dt of x, right, of the position function, will always be the velocity function. And dv over dt, so first time derivative of the velocity function, will always be the acceleration. Okay, so, and this is also equivalent to the second time, not this, the acceleration is also equivalent to the second time derivative of the position function. Okay, so very important things. Thanks for watching.